This is a continuation on page 30, example 3. We didn't get to finish this last lesson, so I'm just going to work on that now. And it says that OABC is a square on the Argand diagram where O is the origin, and the points A and C represent the complex numbers Z and IZ respectively. So we know that with a rectangle, that the angles in a rectangle are 90 degrees, and we know that the side lengths, the side lengths of a square are also equal. So therefore, if we take side OA and rotate it 90 degrees and keep the modulus the same, then that's the same as multiplying by I, hence Z has the coordinates IZ. Now it says find the complex number represented by B. Now remember that a square is also a parallelogram, because a square has 4 equal sides, but it also has opposite sides parallel. So therefore the complex number represented by B will just be, remember if we've got this vector here, OA plus OC, using the parallelogram method, OA plus OC is OB, using that parallelogram method of addition. So therefore B, the complex number represented by B, is Z plus IZ, and it's because of the addition of the vectors of OA plus OB, or plus OC, is equal to OB using the parallelogram method. Okay, so therefore complex number represented by B is Z plus IZ. Now it says that the square, so we're going to form another square. So the square is rotated anti-clockwise 45 degrees about O. So remember OB, this is the diagonal actually of the square. I should have drawn that with a ruler. And we know that the diagonals of a square bisect the angles of a square. So we know that this is 45 degrees, and so is that there. So it says that the square is rotated anti-clockwise, so this way, 45 degrees about O, to form the square OA-B-C- and back to O. And then it says find the complex numbers represented by A-, B- and C'. So what I'm going to do, I'm going to draw the new square. The original square is in black, and I've just put the vertices of the original square in black, and they are O, A, B, C. And the new square, which has been rotated 45 degrees, has vertices O. Now this A has moved across here to A', this B has rotated 90 degrees there to B'. This C has rotated to this position, so this vertex here is C'. So we've got O, A', B', C'. Now we have to write down the complex numbers, or find the complex numbers represented by A', B', and C'. Now we know that the length of OA equals the length of OA'. So therefore, to go from OA to OA', we're just rotating anti-clockwise by 45 degrees. So A' is formed by rotating A anti-clockwise by 45 degrees about O, about the origin. Okay, now we know that that the modulus of OA is equal to the modulus of OA'. Okay, so therefore the length is the same, so therefore A' is equal to Z times 1 cis 45 degrees, which is cos 45 degrees, plus I sine 45 degrees. So to get O', we're just taking the complex number represented by OA, which is Z, and then multiplying it by something of the same length, which is 1. But the argument, we have to add an argument of 45 degrees to it, so we multiply it by Z times 1 cis 45, okay? So therefore, this is going to be Z, cos 45 is 1 on root 2, plus I times 1 on root 2. So therefore, the complex number represented by A', well, I'm just going to put the root 2 out the front because it's a common to both these here. So Z on root 2, 1 plus I. Okay, so that's the complex number represented by A dash. Now to look at the complex number represented by B dash. Now B dash is just B being rotated again 45 degrees to form B dash. So B dash is formed by rotating B 45 degrees anti-clockwise about O. So all the points are actually. So therefore we just take what, and also we know that the modulus of OB equals the length basically of OB equals the length of OB dash. Okay, so I'm just going to focus this a bit better. So therefore B dash will be whatever B is, which is, sorry, B, I should write it on my diagram up here. Sorry, it's off screen. B is, remember, Z plus IZ. Okay, so B dash will be Z plus IZ times 1 cis 45 degrees, which is 1 cos 45 degrees plus I sine 45 degrees, which is Z plus IZ times, this is 1 on root 2 plus I on root 2. Now if we expand that, we will get, what I'll just do, I'll just take the 1 on root 2. I'm just going to factorize out a Z from the first thing here, taking that out as a common factor. So I've got Z 1 plus I times 1 on root 2, 1 plus I. Okay, just pulling out a common factor from each of those. So I've got Z on root 2, 1 plus I squared, which is Z on root 2. 1 plus I squared is 1 plus 2I plus I squared, which is minus, also plus I squared, which means Z on root 2, basically 1 minus 1 is 0, so times it by 2I, okay? Which is, 2 on root 2 happens to be root 2, so it's root 2 ZI, okay? That's what B dash is. Now, I'm going to need some room for C dash. I might just do it up there. Now again, C dash is formed by rotating C 45 degrees anti-clockwise. So C dash will just be whatever C is times 1 cis 45 degrees. Now because we've already worked out what 1 cis 45 degrees is down here. So C is IZ times, now 1 cis 45 degrees is 1 on root 2 plus I on root 2. Okay, now if we simplify that, we can take out the root 2 as a common factor. We've got I'll just go Z on root 2 and then just multiply each of these by, so Z, take the root 2 out as a common factor. I times 1 is I plus I squared, which is minus 1. Okay, so that's what C dash is, Z on root 2, I minus 1. So they're the complex numbers represented by A dash, B dash and C dash. Now for the last part of the question, it says that E is the point of intersection of the diagonals of the square O. So E is the point of intersection of the diagonals of the square O, A dash, B dash, C dash. So if we draw the diagonals of a square, we know that properties of a square diagonals bisect each other at right angles. So if we want to find the intersection of the diagonals of a square, it would either just be the midpoint of O, B dash, or it would be the midpoint of A dash, C dash. So I think it's easier to do that, say that E is the midpoint of O, B dash, reasons diagonals of square bisect each other. So to do midpoint of O dash B dash, it's just using the midpoint formula. So we've got the coordinates here of B dash. So now actually we won't use the coordinates. What we're going to do, we know that if that's OB dash, then halfway along OB dash will be E, because the length OE is half of the length OB dash, and it's along the same vector represented by OB dash, okay? So therefore OE will just be a half of whatever OB dash is, okay, because it's got the same angle there. So therefore it's just a half of root 2 ZI, which is now root 2 on 2 is 1 on root 2, so it's ZI over root 2. Sorry, that's running off screen. So again, OE is represented by half the length of OB dash, which is a half of root 2 ZI, which is ZI on root 2. Okay, now that's the end of that question. We're going to the next page, page 30. Sorry, page 31. Now this is just straight from your textbook, okay? So geometrical representation of complex numbers as a vector. Now, a vector is a mathematical object that has both magnitude, which is size, and direction. For example, if we say a 5-degree increase in temperature, that's a vector quantity because you know that the magnitude or the amount is 5, and the direction, because it says increase, that gives you the direction as opposed to decrease being the opposite direction. So you've got magnitude and direction when we say 5-degree increase. Now, complex numbers can also be represented as vectors for which the modulus gives us the magnitude and the argument gives us the direction. So for example, here on our Argand diagram here, where P is the point Z, which is x plus yi, we know that we can represent Z by the vector OP dash. Notice we write the O, then the P, and the arrow goes forward, saying that we're going from O to P. And the length of OP, the vector OP, is the modulus of Z, and the direction is given by argz, which is whatever the rotation is from the positive direction of the real x-axis. Okay, so in this case, it's up here. Now we can see in the diagram, say down in this diagram where we've got point P here. Now if this is the point, if this point P represents the complex number -1 plus 3i, so this point P is -1 plus 3i, and if Q, for example, so I'm just going through this, so therefore that's represented by the vector OP, okay? And Q represents the complex number 2 cos minus pi on 4. Now that's cos of minus 45 degrees plus I sine minus 45 degrees. So this angle here is minus pi on 4 because it's going in the negative direction. Okay, now 2 is the modulus, okay? And the argument here is minus pi on 4. So here, the vector OP represents this complex number, -1 plus 3i, so the vector OP, with the arrow going from OP to O to P, and the vector OQ represents this complex number, 2. Now, 2 actually will be the length of that vector, and minus pi on 4 is the argument, okay? Now, the vector to represent a complex number doesn't have to start at the origin. For example, see if you look over here, this point 1, 2, that means go across 1 and up 2i. So the point P, represented by 1, which is really 1 plus 2i, that has a length. If I was to draw a right angle triangle here, the length here is 1 and the length there is 2. So therefore, this the hypotenuse, or the modulus here, is the square root of 1 squared plus 2 squared, which is the square root of 5. So therefore, that is represented, can actually be represented by any vector with a length of root 5 that is inclined at this angle. Now the angle is tan theta is 2 on 1. That's actually not the angle. The angle is theta is tan to the -1 of 2. So that's what that says here. So as long as you draw any vector with a modulus of root 5 and an angle inclined at tan to the -1 of 2 to the x-axis, then these vectors represent both the same thing. Now, but they're just called different things, okay? So both OP, the vector OP, and the vector AB represent 1 plus 2i, but point B does not represent the point 1 plus 2i. Point B does not, okay? However, point P does, because it starts at the origin. So point P is the complex number 1 plus 2i. But point B is not the complex number 1 plus 2i. But they don't represent the same complex number, those 2 points, but they represent the same vector. So, as I said, point P represents 1 plus 2i, but B does not. OP is called a position vector because it starts at the origin, and AB is the same vector as OP, but it's not called a position vector, it's called a free vector. Now, when we draw up our parallelograms, when we're adding vectors, we move one of the vectors to form the parallelogram, and that then becomes the free vector once it gets moved, okay? Now notice that AB represents, AB is different to saying BA, okay, because AB and BA with vectors are actually the reverse of each other, okay? So if AB represents 1 plus 2i, then the reverse BA represents, so BA will represent the negative of 1 plus 2i, which is negative 1 minus 2i. So it's really important to note the direction in which you're drawing the vector and which way the arrow is going, because they mean different things. So this way is 1 plus 2i, but that point is not 1 plus 2i. Going backwards is minus 1 minus 2i. Now, operations on complex numbers represented as vectors. Now, we've looked at this before. We did this earlier, I think last week, that when you add vectors. So just going to go through this again. So operations on complex numbers represented as vectors. So when we're adding vectors, so to form the vector sum P plus Q. So let's say I've got P here and I've got Q there. We're organizing this in the tail to tip method. So there's P. I'm going to move this Q up there so that at the tip of this, I put the tail of that. So there's Q translated up there. And because I've started here and I've finished there, then my resultant vector, this one here, is P plus Q, okay? So that's that one. Now, if we want to add P and say Q here, remember the other way, so there's Q there, let's put them both with their tips located here, okay? Also, sorry, the tail located there. So we've got P there and we've got Q there. Now to form the parallelogram, we move this Q up here as well. And then we go from this starting position here to that opposite corner to form P plus Q. So this here in red is P plus Q. This represents Q and this represents Q. Okay? Now we did that last lesson. Now that's addition. Okay? Now with subtraction, it's a little bit different, okay? So the first method where we're doing tail to tip. So we're trying to do P minus Q. Now remember P is that vector here, goes in that direction. So P looks like this and Q, we can see down here, looks like that. So if we want to do P minus Q, we have to do P plus minus Q. So there's P, and if we're going to use, sorry, here is parallelogram method. So we've got P, if that's Q, minus Q goes back like this. So there's minus Q. Notice we've formed them both from this point. Then we've constructed the parallelogram, okay? And then gone from here to the opposite corner. And therefore, going this way, this will be P minus Q or P plus minus Q, which is the same as P minus Q. And using the parallelogram method down here, we know that P looks like this and Q looks like that. So we're going to be adding P with minus Q. So there is P. If you look at what they've done here, they've actually got P there and Q. This is the normal positive Q across here. So it means that this direction up here would be P plus Q. So remember with parallelogram, they're both going out from that corner there. We've got an arrow going there and an arrow going there. So we've got P there and we've got Q going that way. So this diagonal here is P plus Q. The actual other diagonal going the other way is P minus Q. Now, to make sure that we get that right, see this P, I'm actually going to draw it here just to get the direction of the, actually I'm going to do it here. So if I've got P there and this is Q and I want minus Q goes like this, right? So therefore the addition, if I form my parallelogram over here, then P minus Q is this vector going like that, which happens to be this one here, which is what they've got on the diagram. So therefore this here is P minus Q. So the vector for the sum P minus Q is this diagonal here of the parallelogram that goes from the tip of the normal Q to the tip of the normal P, okay? Now, sometimes it's a bit hard to work out the P minus Q one, so you might want to draw the normal P and draw the negative Q, the minus Q, and then do it as the sum going out like you normally do a vector sum, okay? Page 32, and this is just from your textbook as well. Now it says let A represent Z1 and B represent Z2. Now when we use the parallelogram method, so A is Z1, we've got our arrow going this way, and B is Z2. So the vector OB represents Z2, the vector OA represents Z1, okay? Now it means that the vector OC going that way represents, because we're forming the parallelogram with the corners here and going out there, and then we form the parallelogram like that. So OC, the vector OC represents Z1 plus Z2. Now, this vector AB represents Z2 minus Z1, so the vector AB. So let's just see how that works. I'm going to draw that down here because it's a little bit hard to tell from there, okay? So I'm just going to draw these again. If it says that the vector AB, so from A to B, represents Z2 minus Z1, let's have a look. This is Z2. Z1 is this. So if that's Z1, then minus Z1 looks like this. That would be minus Z1, okay? And so Z2 minus Z1 forming the parallelogram would go in this direction, okay? So therefore AB, and that is in the direction of AB, okay? So even though our AB is there, we can see if we do Z2 minus Z1 there, and we draw this as our resultant of Z2 minus Z1, that vector is going in the same direction and has the same magnitude as this vector. So therefore, AB represents Z2 minus Z1. Now, if from A to B represents Z2 minus Z1, then the vector BA will represent Z1 minus Z2. Now, let's have a look. This is for vector AB, okay? Z2 minus Z1. Let's look at forming the vector BA. They're saying it's Z1 minus Z2. Let's have a look. Z1 is like that. So I'll just focus this. Now the normal Z2 is like this. So minus Z2 would be like that. So forming the parallelogram, this would be Z1 plus minus Z. Laptop just died, but I've just got it back on. So I'll just go back to where we were here. We're trying to do Z1 minus Z2. Now we know Z1 is this vector, and we know that Z2 is that vector. So therefore minus Z2 would be in this direction. So forming up the parallelogram and coming out here, this would be Z1 plus minus Z2, or just Z1 minus Z2. Now if we look at the direction of that, that is the same vector as this, BA. So BA is Z1 minus Z2, okay? Now, coming back up here. The modulus, see, OC represents Z1 plus Z2. So the modulus of Z1 plus Z2, or this length, which is the length of the diagonal of this parallelogram, so Z1 plus Z2 and Z1 minus Z2 happen to be the lengths of the diagonals of the parallelogram, okay? and argument of z1 plus z2, which is this one. And so the argument of z1 plus z2 is the angle at which the diagonal is inclined to the positive direction of the real axis. And this one up here, see this is the other z1 minus z2. If you bring this down, remember the angle that it's inclined with the positive direction, with the real axis can go, remember arguments go from 0 to pi, or from 0 to minus pi. So this is the argument for z1 minus z2. So it's this angle down here, because we can't cross the x-axis down here. So just extend this line down here, and this bit down here is the argument of z1 minus z2. So therefore, these arguments give you the angles at which the diagonals are inclined to the positive direction of the real axis. The first one's going anti-clockwise and the other one's going clockwise, okay? Because arguments must go between 0 and pi, or 0 and minus pi, okay? Example 4, it says on an arcgan diagram, let A represent Z1, which is 3 plus 2i, so A represents Z1, and B represents Z2, which is negative 2 plus 4i, okay? So I've just drawn them in approximate positions. So I'm going to draw OA here, and I'm going to draw OB here. Now it says, show the following, point C which represents Z1 plus Z2. So I'm just going to use parallelogram method here. We're going across 3 and up 2. So we're going across 3 and up 2. So just drawing a parallelogram here, just trying to draw it roughly the same. So this is, I'll just try and get the same length. So across 3 and roughly up 2. So this is Z1 transposed up there, and then just completing this parallelogram here. Sorry, it's not, I think I've drawn that a bit long, so I'll just draw this, close this up here. That is a bit long, okay? So completing the parallelogram, if that's OA and that's OB, then this up through here is the vector OC, and it represents, the vector OC represents the point, so this point C represents Z1 plus Z2. Okay, so this is Z1, this is Z2, okay, and this, by using that parallelogram method, is Z1 plus Z2. So the point C represents Z1 plus Z2. The vector that represents Z1 plus Z2 is OC. So OC represents, so that point C represents Z1 plus Z2. The vector OC represents Z1 plus Z2. Now the vector that represents Z1 minus Z2, so if this is Z1 plus Z2, this other diagonal will be Z1 minus Z2, but you've just got to get the direction correct. Now if you've got Z1 minus Z2 and you then completed the parallelogram, it goes this way. Okay, so just pretending that you're bringing minus Z2 here, the arrow would be that way. And if you completed the parallelogram and did the diagonal, it would go downwards. So therefore, the vector that represents Z1 minus Z2, see, look, Z1 minus Z2 is going to be the vector BA. Represents Z1 minus Z2. Okay, now the point that represents Z1 minus Z2, you'd have to draw it to be able to do that. So if I do Z2, now remember Z2 is minus 2 plus 4i, so it would be plus 2 minus 4i down here. So Z minus Z2 would be down here. Okay, this is minus Z2. And if I were to draw the parallelogram and complete it, I would get this. So therefore Z1 minus, sorry, you can't see this. So Z1 minus Z2 would be this, or the point. So that's the actual point, Z1 minus Z2. This is the vector BA represents Z1 minus Z2. So does OD. It actually also represents Z1 minus Z2. So the point D, there it is down there, that represents Z1 minus Z2. But the vector BA also represents Z1 minus Z2, and also the vector OD also represents Z1 minus Z2. They both do, okay? Now, because one of them, this is the position vector and that's the free vector. Okay, now the point E, that represents a half of Z1 plus Z2. Now there's Z1 plus Z2 along here. Point C is Z1 plus Z2, or the vector OC represents Z1 plus Z2. So remember, halfway across, the diagonals of this is it's a parallelogram, and the diagonals of a parallelogram bisect each other. So the point E is here. It will be the intersection of the diagonals. So E is the midpoint of diagonal OC, because it's a half of what C is, or half of what OC represents, a half of Z1 plus Z2. So that's point E there. Now, what complex number is represented by the vector from E to B? So the vector E to B. Now, if E is half of Z1 plus Z2, then the vector represented by EB is, now I'm just going to draw EB. So there's E to B. What's this vector represented by? Now, if you can try it by addition of vectors or subtraction of vectors, you can try it like that to see what it would be represented by. I prefer to use the tail to tip, like the physics method, to do this particular one. So if that's my resultant vector EB, if I start from this point, and if I start here and if I go down here and add this onto it, so if I go down there and add this onto it, so what I've done, I've gone down and across here. Now, using that physics addition of vectors tail to tip method, go that vector, sorry, I'm off screen, plus that vector there is this resultant vector. Now that's what we're trying to get there, okay? So this vector down plus that vector up there is this resultant vector there. Now, if this from here to there is a half Z1 plus Z2, then the vector coming down here is minus a half Z1 plus Z2, okay? And then this vector up here from O to B happens to be vector Z2. And this is our resultant vector, which is EB, okay? So therefore EB is so therefore it's minus a half Z1 plus Z2 plus Z2 plus this one. Or you could just really say that that is Z2 minus a half of Z1 plus Z2, okay? So I'm just, otherwise you've got to try and form a parallelogram where this is the diagonal of the parallelogram, okay? I think it's easier to do that tail to tip method. So this is the first vector, then the second one, and that's the addition of the two, okay? Now, the last question says, part G, it says what geometrical relationships are there between the intervals EB and DO. There's DO, okay? Now, EB and DO will be parallel to each other. So this is for part G. So EB and DO are parallel to each other, but EB will be half the length of DO. So EB is half the length of DO, and we know that EB is parallel to DO. Okay, because remember, this vector OD is Z1 minus Z2, and so is this vector BA. It's also Z1 minus Z2. And we know that EB is lying on that vector, so the direction is the same, so therefore they'll be parallel. Okay? Now continuing on page 33. Now it says, here, example 5, okay? It says, in this arcane diagram shown below, OP, so from O to P, now I haven't drawn that in, represents the complex number Z. So I'm just going to put a Z here at, well, OP, I better draw it like that. So OP represents the complex number Z, okay? Label each of the vectors CP, so we're going from C to P. Now C is actually the point 0,3. PA, so P goes from P to A, so the tail is there and the tip is there at A. Now A happens to be the point 0,1. The vector D to P, so the tip is up there. DP, now D is the point 0,3, is that vector from D to P with the arrow up there, and BP is this from B to P with the arrow up there, and B happens to be the point -4,0. Okay, now it says, in the arcane diagram below, OP represents the vector, the complex number Z. Okay, so from O to P is Z. I'm just going to put a Z there or just along here. Okay, now label each of the vectors CP. So we have to label CP, PA, DP, and BP with the complex number that they represent. Now, let's start with the first one, CP. So, if this is Z and C, to get to C, it's 0 across and 3 up, then point C, so if C is 0, 3, then OC is the vector 3i. Okay, now how do we get CP? Now, if we start and we go like this and then add that, then our resultant vector goes like that, but we want our resultant vector to go like that. So if we start from C and go down to O, so from C down to O, and then from O to P, then our resultant vector will be CP. So I'm going to say that the vector CP is formed by doing vector CO plus vector OP. Now vector CO, so to get resultant vector CP, now this is using the tail to tip physics method. To get vector CP, you go down for CO, so I'll just draw it here, down for CO, across for OP, and the resultant will be this, which is CP. Okay, so CO plus OP will give CP. So I've got that there. So CO, if OC is 3i, then CO is -3i, and from O to P is Z. So therefore, CP is represented by the complex number Z minus 3i. So that's the first one, okay? Now the next one, PA, okay? Now PA, how do we form PA? So I'm just going to draw it along here, PA, P to A. Look, I just have this other diagram here if I needed some more room, okay? I might actually just put this diagram over here so that I've got some room. So that was CP, this was CO, and OP, okay? That was the first one. Now looking at the second one. Sorry, I should just pause the video really. Okay, let's look. We're looking for PA. Goes like this. Now, how are we going to get that as our resultant vector? To form PA, we would start from P to O and then go from O to A. So if we start here, we go PO plus OA gives PA. So PO plus OA gives vector PA, okay? So PO, now we know that OP is Z, so PO is minus Z, plus from O to A is 1, because OA is just real, and the length there is 1. So the vector OA is just 1. So therefore PA is minus Z plus 1, or it's just 1 minus Z. So that's what vector PA is, 1 minus Z. Okay, now let's look at some other ones. I think I'll do the others up here on the diagram. Okay, we're looking for DP. So how do we go from D to P? So we want to go from D to P. Now that's our resultant vector. Okay, so we need to, if we start here and we go DO plus OP gives DP. Okay, so DO plus OP gives DP. So I'll just write that down. DO plus OP equals DP, using that vector, that physics tail to tip method. So if OD, going from O to D is minus 3i. So going from D to O is 3i, okay? And OP is the vector Z. So therefore DP is the vector 3i plus Z, or Z plus 3i, okay? Now for the last one, the vector BP. So let's just draw BP. So how would we form BP? Now that's my resultant vector. So if I start from B to O and then go from, so I'm just going to do that up here actually, just need some room. So B, O, P. If I start from B to O and then I go from O to P, then my resultant vector will be BP, okay? So tail to tip, okay? Tail to tip, there's my resultant vector. So therefore, PB is equal to BO. Now the order is very important. It's BO going that way plus OP. Now OB is minus 4i. So BO is 4i. Okay, sorry, I'm just running off screen again. So again, OB, because B is the point minus 4, 0. OB is minus 4i, so BO is positive 4 plus 4i. OP we know is just the vector Z. So therefore PB will be the vector, sorry, it's not minus 4i, it's just minus 4. Sorry, that was a mistake. So that's the real axis. So sorry about that. Okay, so this is minus 4 along there. So BO is 4, sorry about that, 4 plus Z. So therefore the vector PB is 4 plus Z, or just Z plus 4. Okay, so that's what the vector PB is. Okay. Okay, now just continuing on page 33, example 6. It says if A is the point 1, negative 1, and B is the point 5, 2, I mean, it doesn't have to be drawn perfectly. Okay, and this is the point 5, 2. And this is B. And if A is 1, negative 1, and P is the point 1, 2, root 3, so 1, 2, root 3. I'll just put it up here somewhere. This is the point P, 1, 2, root 3. And if Q is the point 0, root 3, so here, roughly. And this is the point Q, okay? Now, it says, and if they're points on the Argand diagram, so we've got 0, root 3. Find in the form A plus IB the number represented by, now this is A, we want the number represented by AB, the vector AB, so I'm just going to draw that in. And in modulus argument, so we want this in A plus BI form, and in modulus argument form, we want the number represented by PQ. Okay, so going from P to Q in mod arg form. Okay, I'm just going to pause. So just coming back to this question, sorry. Find in the form A plus IB the number represented by the vector AB. Now, if we let AB represent, let's just say z, the complex number z, then we can see by vector addition that AB, the vector AB, is equal to, and I'll just call this point C, for example. The vector AB is equal to the vector AC plus the vector CB. So vector AB is equal to vector AC plus the vector CB. Now, if we look at vector AC, CC is across just from B, and the distance from A to C is 3 units up, and it's going 3 units up the imaginary axis. So from A to C is 3i, and the vector from C to B, we're going from 1 to 5, so it's 4 units across there. So from C to B, we're going 4 units across the real axis in the positive direction. So the vector AB, as we can see, is vector AC plus vector CB, which is 3i, because we're going upwards on the imaginary axis by 3 units and across the real axis 4 units in the positive direction. So it's 3i plus 4 or 4 plus 3i. So therefore that is the vector AB in the form A plus IB. Now we need to look at the vector formed by PQ, and we'll call this Z, I suppose, and we'll call this one, or I'll call that Z1, and we'll call this one Z2. Okay, so we're going to let PQ represent, or PQ represents Z2. Now, we want to do this in modulus argument form PQ. So we're going to need the modulus of PQ, and we're going to need the argument of PQ. Now, we really need to be finding the gradient of PQ, okay? And it needs to be the gradient. So if PQ is going down here, so it goes like this, we need actually this angle here, not that angle there. So what we can do, to be able to find this angle here, we could first say find this angle in here, and I'm going to call it theta. Now if this here is the point 0, root 3, then this distance here is root 3. Now I can also form the triangle up here. So this triangle down here and this triangle up here are similar triangles because we've got right angles and these are vertically opposite. So this angle here is theta as well. Now, this is root 3 up here. This distance is also root 3. And this distance across here is 1, so that's 1. So if I just work out what theta is, so I'm going to go that tan of theta we know is opposite over adjacent, so tan of theta is root 3, so theta is pi 60 degrees, which is pi on 3. Now that's what theta is. This is the angle I need here, okay? Actually, I might call that alpha, actually. I'll call that alpha. So tan of alpha is that. So theta is what I want. Theta is pi minus alpha, which is pi minus pi on 3. Actually, which is, so the size is actually 2 pi on 3. But if we look at that, and if I say move this across here, remember it's the direction from the real axis. What I've really got for here, because it's going backwards in the negative direction, it's actually, theta is actually negative 2 pi on 3. It's not actually, the size, its magnitude is 2 pi on 3, but because this is an angle going in the negative direction, it's negative 2 pi on 3, okay? So that's what the argument of this is. Now just for the modulus, we can just go that, I'll just call that Z2. Modulus of Z2 is the square root of 1 squared plus root 3 squared, which is square root of 4, which is 2. So therefore the complex number represented by Z2 is 2 cis negative 2 pi on 3, which is 2 cos negative 2 pi on 3 plus I sine negative pi on 3. Okay, so that is the complex number represented by PQ. Okay, notice the angle, so I had to extend this line, and this is the angle here, and that's in the negative direction, which is why it's negative 2 pi under 3, not just, this is actually just the magnitude of the angle, so that's just its size of that angle, but taking into account the direction, it's minus 2 pi under 3. Okay, so that's the vector represented by PQ. So in the next video, I'll continue from example 7 on page 34. Okay.